Hello! Today, Lucien and I will discuss two-player zero-sum games in game theory, specifically calculating mixed strategies and average payoffs. To demonstrate, I'm going to take away Lucien's tuition money penny by penny. However, Lucien is trying to do the same to me. My scheme is as follows. I've challenged Lucien to a game of matching pennies. No, not that one. There we go.
The game is this. We each have a penny. We each pick heads or tails and simultaneously reveal our choices. Based on the outcome, we're going to pay each other. We can represent our transactions with this table. If we both pick heads, I pay Amy 1 penny. Her payoff is 1, mine -1. If we both pick tails, I pay her 3 pennies. Her payoff there is 3, mine -3. But if our pennies mismatch, Amy pays me 2 pennies. Her payoff there is -2, mine is 2. This is a zero-sum game. For each outcome, however many pennies I win, Amy loses, and vice versa.
How can I maximize my winnings and Lucien's losses? In the ideal world of game theory, I will boldly assume Lucien is perfectly rational.
Likewise, I will assume Amy is perfectly rational.
Neither of us wants to always play heads or always play tails, because then the other will always know how to win. As I am perfectly rational, I have this great strategy where no matter what Lucien picks, heads or tails, I won't benefit more from changing my strategy, meaning my average payoff won't be higher. My strategy is to pick heads with a certain probability x, and thus tails with a probability 1 minus x, as the probabilities must sum to 1. This is called a mixed strategy, as I have multiple choices, and am choosing between them with fixed probabilities. Lucien will likewise have a mixed strategy of picking heads with a certain probability y, and tails with a certain probability 1 minus y, so no matter what I pick, they won't benefit more from changing their strategy. This is called a mixed Nash equilibrium, which is where I can't do any better by picking heads or tails with different probabilities, and neither can Lucien with their probabilities.
Let's take a look at Amy's average payoffs. If she picks heads, she has a y probability of winning 1 penny and a 1 minus y probability of losing 2. So she will get 3y minus 2 pennies by playing heads. If she picks tails, she has a y probability of losing 2 pennies and a 1 minus y probability of winning 3. So she will get -5y plus 3 pennies by playing tails. Because we have reached a mixed Nash equilibrium where I pick heads with a certain probability y and tails with a probability 1 minus y, I don't benefit more from changing those probabilities. Thus, over the course of many games, regardless if Amy plays heads or tails, I get the same average payoff. Likewise for Amy, her average payoff is the same regardless if I play heads or tails. Because of this, we can set the equations for her average payoffs for heads and tails equal to one another, and solve for my probability such that this is true. For my average payoffs, we can similarly write expressions for my payoff based on Amy's mixed strategy, and set those expressions equal to each other to solve for her probabilities. Thus, I pick heads with probability 5/8 and tails with probability 3/8.
And I pick heads with probability 5/8 and tails with probability 3/8.
Now, is this game really fair? Let's talk about average payoffs.
Suppose we have players P and Q, and for both players, choice 1 is heads and choice 2 is tails. So P has P1 probability of playing heads and P2 probability of playing tails, and Q has Q1 probability of heads and Q2 probability of tails. We can represent these mixed strategies as vectors P and Q. Let A sub P be the payoff matrix for player P, where the Aij entry of A sub P is the payoff for P if P chooses choice I and Q chooses choice J. Looking at it from Q's perspective, we have this table where the rows represent Q's choices instead of columns. So Q will have a different payoff matrix A sub Q, where the Bij entry of A sub Q is now the payoff for Q, but still if P chooses choice I and Q chooses choice J. Then the average payoff for P is P transpose times A sub P times Q. How come? When we multiply out the expression, we get a sum of terms. Each term is the payoff of an outcome for player P times the probability that the outcome will occur. For example, for the first term, we have the probability P chooses heads times the probability Q chooses heads times the payoff for P when both players choose heads. Summing these terms gives the average payoff for player P.
Back to our game, let me be P and let Amy be Q, with the mixed strategies that we calculated earlier represented as vectors P and Q, and our payoffs represented as matrices A sub P and A sub Q. Calculating our average payoffs, I gain 1/8 of a penny per game, and Amy loses 1/8 of a penny, but Amy can't do any better from changing her strategy.
Bamboozled.
So, I gain infinite money. Anyway, thus concludes our presentation on game theory, and how to very slowly win pennies from your friends.
Thanks for listening. Any questions?